Let's talk about projections. The logical way of our understanding this idea of map projection consists of several steps. First of all, reference surface. The reference surface is the surface to which all our geodetic measurements should be projected. There are several reference surfaces such as geoid and ellipsoid. The geoid is the first reference surface to be examined, which is sometimes referred to as the mean sea level rise above or below the ellipsoid. In the right, in the pictures, you can see mathematical feature of ellipsoid. A red line means geoid, and different kind of heights from our geodetic control point to these reference surfaces. In the colorful picture, you can see a geoid model with parts of our planet of the geoid surface which are below in blue and above in red ellipsoid surface. There are different ellipsoids which has been made by different mathematical procedures, and first of all the global ellipsoid and the local ellipsoids. We should speak about vertical datum, which constitutes a reference surface for vertical positions and also known as height datum, is of kind of stated below. The local vertical datum and global vertical datum. The first kind of vertical datum for our discussion is the learning path is the local vertical datum, also known as the local height datum, and sometimes regarded as an approximation to the geoid. Local vertical datum takes us to the next kind of vertical datum in this learning path, is known as the global vertical datum of global height datum. Global vertical datum is also known as geodetic datum, constitution our next concept. While vertical datums explain the heights above sea level or above ellipsoid, the horizontal datum, just like the explains how can we measure the position of a point on the Earth's surface. We also should understand the conceptions of local horizontal datum and global horizontal datum, which help us understand the How can we explain the position of any point globally on the globe surface or in a local point neighborhood near our point of interest. We use in geodesy a few projections. We should speak about different coordinate systems. First of all, latitude and longitude. And the map projections explain how should we project coordinates of local points to the plane map. There are many different species of map projections, and later we should speak about these classifications, projectional classifications, and coordinate transformations. Well, in this map, we can see small red points, which explain how to what is the tide gauges we use as 0 points of our Heights models. These points on a map Kronstadt, for example, in near St. Petersburg in Russia, it is a 0 level for all Heights systems. In the post-communist states, the map shows this Height system in light green. Another 0 points or tide gauges, Aarhus in Denmark, Amsterdam for Netherlands and Germany, Ostende for Holland, Yulin for Great Britain, Marseille for France, Genoa for Italy, etc. Every nation or group of nations have established those mean sea level points which are normally located close to the area of concern. We can determine the height of a point in the Netherlands or Germany with respect to the Amsterdam tide gauge using a technique known as geodetic leveling. The result of this process will be the heightable local mean sea level. The height determined with respect to tide gauge station is known as the arithmetic height above the geoid. Obviously, there are several realizations of local mean sea levels, also called vertical datums in the world. They are parallel to the geoid but offset by up to a couple of meters. The offset is due to local phenomena such as ocean currents, tides, coastal winds, water temperature, and salinity at the location of tide gauge. Care must be taken when using heat from another local vertical datum. This might be the case in the border area of adjacent nations. An example, the tide gauge zero height of the Netherlands differs more than 2 meters from the tide gauge zero height of the neighboring country, Belgium. In the picture right here. Even within a country, heights may differ depending on to which the tide gauge mean sea level points they are related. An example, the mean sea level from the Atlantic to the Pacific coast of the USA increases by 0.6 to 0.7 meters. In this fragment, you can see brown lines which don't correlate with counterlines in the Netherlands, in Belgium. So these two countries use different 0 points for heights measurement. In the picture, you can see how this equipment is working. You can see global navigation satellite system antenna. Vertical land motion can be measured by this equipment. Tide gauge can measure local mean sea level, and this is 0 point level in Amsterdam City Hall. The local vertical datum or height datum is implemented through a leveling network as shown in the picture in the right. A leveling network consists of benchmarks whose height whose mean sea level has been determined through a geodetic leveling. The implementation of the datum enables easy user access. The surveyors don't need to start from scratch from the Amsterdam tide gauge every time they need to determine the height of a new point. They can use a benchmark of the leveling network that is closest to the point of interest. Benchmark of the leveling network, you can see small circles in the picture. The level equipment consists of just level instrument and the rulers, which can help to go step by step and understand the height difference between start and end points. The use of satellite-based positioning, for example, GPS, to determine heights with respect to a reference ellipsoid. For example, World Geodetic System 84 is becoming more in use. These heights are known as ellipsoidal heights. Heights above the ellipsoid. Ellipsoidal heights have to be adjusted before they can be compared to arithmetic mean sea level heights. Geoid undulations, you can see N letter in the picture, are used to adjust the ellipsoidal heights. As a result of satellite gravity missions, it is currently possible to determine the arithmetic heights. with centimeter level accuracy. While we are speaking about coordinate system, first of all, it is Cartesian coordinates for the whole Earth. These coordinates are calculated from the axis x and y axis lays in the equator, and the z-axis is equal to the Earth's rotation axis. Geographic coordinates phi, lambda, and z, which mean latitude, longitude, and altitude. Projected coordinates x, y, z on a local area for the Earth's surface in map projection. And the main idea of projection process is how to recalculate latitudes and longitudes to the local projected coordinates. We should remember that z coordinates in first and third systems is defined geometrically, and in the second systems, z coordinate is defined using gravitation potential. Here, global Cartesian coordinates x, y, z axis. Map projection is a term used to describe a broad set of transformations employed to represent the two-dimensional closed surface of the globe on a plane. For example, you can see a Miller cylindrical projections when we are projecting the globe's surface to the cylinder surface. There are different tangent and secant projections: cylindrical, conic, and azimuthal. Gauss-Kruger projection we use for topographic maps. It is a main projection in former Soviet Union states and post-communist states. All geodetic works needs special kind of geodetic projections which preserve the angles on ellipsoid and on a map. The design of the surface of the Earth's ellipsoid is carried out on the side surface of a tangent cylinder in zones with a length of 6 degrees longitude. There are 60 zones in total. An imaginary cylinder covers an ellipsoid along the meridian called the central axial meridian. The zones are counted from the Greenwich meridian. Numbering goes from west to east. In each zone, the axial meridian and the projection of the equator line serve axis of rectangular coordinates. This projection has name of Carl Friedrich Gauss. It is a famous mathematician, astronomer, and physicist considered one of the greatest mathematicians of all time, or the king of mathematics. You can follow the link and see a small example, a small part of Hollywood movie about Carl Friedrich Gauss measuring the world. And in this small fragment, you can see young Carl in his school. Adalbert Krüger, another famous German astronomer, he was chief assistant, served as worked as a director of the observatory at Helsingfors, Kiel, and Gotha. He used Gaussian equations and has proposed to use these projections for geodesy. The Gauss projection is equal angle traverse cylindrical projections. It preserves the angle at the globe and in the map are absolutely equal. Since the territory of Ukraine is completely located in the northern hemisphere, all values of x coordinates in the will be positive. In order for the coordinate y to be always positive, an Eastern offset or false easting is introduced. An artificial shift equal to 500 kilometers, so that at the beginning of the coordinates at the value of y is 500 kilometers. To exclude the same coordinates, a zone number is placed before the y value. Similarly, in the southern hemisphere, the northern displacement, false northern, equal to 10,000 kilometers, is introduced for the same purposes, so that at the beginning of the coordinates, the value is 10,000 kilometers. In addition to the Gauss-Krüger projection, the cutting straight cylindrical Mercator projection is used as a geodetic projection with which is a type of Gauss-Krüger projection. The design is also carried out in zones with a length of 6 degrees longitude. In each zone, the axial meridian and the projection of the equal line are axes of rectangular coordinates, but because of the sequential type of projection, the scale is equal to 1, not on the axial meridian, but along two thick lines 180 kilometers away from it. You can see axis meridian, red point, and the lines of equal scales. Zone numbering is from the dateline in UTM projection. An abscissa of Gauss coordinate Krüger is similar to Gauss Krüger coordinate Here you can see UTM coordinate zone numberings. Each cell in the grid has its number and letter. Here you can see the explanation of this projection for GIS systems, how to define parameters in digital environment. And in this picture, you can see difference between Gauss-Krüger projection and UTM projection.